Thank you. Does this work? All right. Hi, I'm Hassan from Macquarie University, Australia, and this is a joint work with my colleagues Robin, Ben, and Dali. So this work, we were interested in providing privacy to user-submitted text to AI. And in order to provide privacy, we work with word embeddings. So what are word embeddings? This is a process that converts words into high-dimensional vectors. So each word will be converted into a high-dimensional vector in an embedding space. And one of the characteristics of this embedding space is that it maintains relationships between words in the embedding space. And how do we use that to provide text privacy? We take each word at a time in the prompt. We convert that into a vector. We add noise to that vector. And then we try to find the nearest word in the vocabulary and output that. So from a privacy point of view, the intuition is that we replace the original word. Utility point of view, we replace it with a synonym. So here's an example. On the left is an example user prompt, and I've highlighted the sensitive terms in red. We apply dX-Privacy word by word, and you can see it's a bit gibberish, but that's not a problem because we can give it to a large language model to restore as much as possible. And as you can see at the end, we have a coherent prompt, and with the advantage that some of the sensitive words are not reconstructed. So when we tried this mechanism on text, we saw an unusual behavior. So on the left is the canonical Laplace mechanism in one dimension. So as you can see, with small epsilon, a distant value is output most of the time by the algorithm. As we increase epsilon, we get nearer values to the original value being output, with the smooth transition ending in the original value being output as we increase epsilon, which is the usual behavior. In the case of dX-Privacy, on the other hand, for text, we either saw that distant words were being output, or only the original word was being output as we increase epsilon. And none of the, or very seldom would we see a nearby word. So there was no smooth transition, and this is really bad for privacy utility trade-off because we either get no privacy, the original word, or we get no utility, a very dissimilar word being output. So you might think this is because of Euclidean distance, because it is known to cause some issues in high dimensions, but in this case, this is not straightforward because text embeddings are trained to make sure that nearby vectors in high dimensions are semantically similar. You can check this link for some details as well. So our goal in this paper was to find why this was happening. Was it because of the definition of dX-Privacy? Was it the particular mechanism we were using, or was it high dimensions? And if possible, to come up with a fix. So just to recall the definition of dX-Privacy, it ensures that the output of a mechanism on two inputs are close in probability, and this closeness in probability is not just dictated by epsilon, but also by the distance between those two inputs. So the advantage over ordinary differential privacy is a better privacy utility trade-off. For example, in the case of location application, ordinary differential privacy will ensure that all points in the map are indistinguishable. But in the case of dX-Privacy, we're more concerned about privacy for nearby locations. All right, so this is the Laplace mechanism that we are all familiar with. And it works by drawing noise from this Laplace distribution. There's also a higher dimensional counterpart of this called multi-dimensional Laplace distribution. Has two components. One is the angular component, which is obtained by drawing a random point on the surface of the hypersphere, and it also has a length component, which is drawn proportional to the negative exponential. So you multiply those two and we get a multi-dimensional Laplace distributed variable. So how do we use that for privacy? We draw a noise from this multi-dimensional distribution. We add it to the word embedding. Almost always it will land in the embedding space which does not belong to an actual word. So we try to find the nearest word in the vocabulary and output that. So what is going on? So here on the left, I've got the original word W, and X is the nearest neighbor, and that blue point is the midpoint between these two. The noise distribution would have a projection. If the length of this projection is less than that blue dot, then the original word is output. If it's more, then the nearest neighbor is output. So this gives rise to this equation on the left. And I've got capital Z as the noise projection distribution. And similarly, we can also obtain an equation for any two neighbors of the word W. So this dictates if X or Y will be selected as the output by the mechanism. So what we found was, on average, when we apply this mechanism, the original word is output most of the time, or is the nearest to the noisy embedding, followed by the next neighbor of W, followed by the second nearest neighbor, and so on. In other words, the mechanism was actually working as it should. But the difference is that in high dimensions, the nearest neighbor to a word is more distant than the relative difference in the distances of any two neighbors. Which means what happens in high dimension is every word is isolated. So with large epsilon, we would perturb it to a word whose closest, to a vector whose closest neighbor is the word itself. As we increase epsilon, as we decrease epsilon, the noise carries it to faraway place where all the different words, not just the neighbors, are located. So we don't get any smooth transition. This also tells us a way to fix it. So if we can flatten those distances somehow, then we would be able to fix this issue. So what we can do is arrange the points according to their nearest neighbor distance and then sample proportional to that distance. But the problem is this is not a distance metric, so we can't use it as a dX-Privacy mechanism, but we can use it as a post-processing step. So here we can see that we indeed recover what the mechanism should do. The green line here shows that the nearest neighbors are also being output by the mechanism at some epsilons. Here C is a constant which needs to be fixed for each vocabulary, but this is just a pre-processing step, so you only need to do it once. This might look similar to the exponential mechanism. But we show in the paper that the exponential mechanism also suffers from the same issue, and that's because it's using the Euclidean distance. To conclude, we show an issue with the multidimensional Laplace mechanism, and we tie it to the nearest neighbor search. We also show a fix, and we have also shown that this problem persists in other mechanisms like the exponential mechanism. Question is, are other dX-Privacy mechanisms also have the same problem? And one interesting line of work, I think, is to find word embedding models or train word embedding models that work intrinsically with noise generating mechanisms. And that's the last slide. I do not have a poster, but I'll be standing over there with my laptop if you guys have any questions.